Testing 1, 2, 3. Welcome. Today is March 17th, Tuesday. If you can hear me, please let me know in the chat, as I just changed my microphone settings. No response. Hello? Alright, well, today we're going to continue on where we left off with electric fields. We looked at the field map itself, the drawings. Hopefully you got that finished. And then, let's do a couple of examples. From our PowerPoint, we did this one yesterday, where we found the electric field by dividing the force by the charge Q, and we saw that yes, the direction of the field is also the same direction as the force. F equals EQ, or E equals F over Q, only works if you know what the force is. Okay, what if you didn't know the force? So if we have, let's use black. There we go. If you have a charge that is on the y-axis up top here, we can say that it is, let's see, 4 nanocoulombs, plus 4 nanocoulombs. Okay, and currently it is 1, 2, 3, 4, 5. Oh, I wanted to do 5. Darn it. Let's do 5. There we go. 5 ticks, or 5 ticks up. And then 1, 2, 3, 4, 5. And we want to find the electric field at this point. Maddie, can you hear me? Is this working? Since you are here. Oh, okay. So we're going to find the electric field at point X. Now, this is similar to what we did before with forces, except when we used forces, there were 2 charges. And so we found the interaction between the charges, etc., etc. Here, we're trying to find E, the electric field itself. The field gives you the value of space, not an interaction between 2 things. It's the value of space, which basically means that if I did have a second charge, I can figure out easily what the force on that second charge would be, knowing what the value of space is at that point. So this blue dot is not another charge. This is just a point in space. A point in space. And so on that spot, which way does the electric field point? Right? So that's the question. Now generally we know that if it's a positive charge, all the field lines are pointing away from the positive charge in all directions. Okay? So the electric field would be pointing away in that direction. So at that spot, we also have a vector that points away, like so. So this is what we're looking for, the value or the magnitude and direction of this arrow. So this is the E we're looking for. We'll call it EX. Okay, So again, it's not an interaction between two charges. It's just the field strength a certain distance away from our positive 4 nanocoulomb charge. Now, if this were 1, 2, 3, 4, 5, so let's say it's 5 centimeters in 5 centimeters, like so. How far is it? If you can pull out your calculators now. So this is, if you can see, it's a triangle, and it's 5 by 5. So what's the hypotenuse? What's the hypotenuse, chat? You guys awake today? Was it harder to get up? Did you stay up late? Is that why? Alright. Of course, if I use the Pythagorean Theorem, square root of 5 squared plus 5 squared, square root of 50. You stayed up late, Christian Tran? That's not good. You know, pretend like school is in session, right? On a weekday, you don't, it's not summer yet, so on a weekday, you want to go to bed at the same time you do normally. This is a 5 rad 2 centimeters. Okay. So we know that our point is 5. Ooh, there it is. There it is. Good job. 5 rad 2 centimeters. Christian Trend, you get a wireless high five. How do I do an emote? Is there an emote? Slash high 5. No, I don't have a high 5 emote. Do I? Nope. If anyone knows how to do a high 5 emote, let me know. Good morning. Don't know who you are though. Alright, so we know that the distance here is 5 rad 2, and our goal is to find the electric field at this point. So we'll use the general formula for electric field. Remember, yesterday we used E is equal to force divided by Q. That only is good if we know what the force is, but we don't. The general formula is based on the general formula for force. Right? You know that the force is KQQ over R squared, and now we are dividing that by Q. So this is the force equation. And then dividing it by Q gets rid of one of the Q's. And so the general formula for E is just K single Q divided by the distance squared, R squared. You can use D squared if you want. Doesn't really matter if you use D or R. Oops. What happened? There we go. D or R is the distance from the charge. Alright, so the distance from charge D, and now it's just a simple plug and chug. So K is still 9E9. The charge is 4 nanocoulombs. Alright, how many coulombs is that? Chapito, do you know? How many coulombs is 4 nanocoulombs? I'll give you a hint, starts with a 4. Nano is 10 to the negative 9. Moderator deleted. Why? That is weird. Oh, I started setting up Streamlabs and auto moderators, so it blocks people if you do stuff. What are you typing anyway? Actually, I need to turn that off. Let's see, Streamlabs, CloudBot, excessive symbols, right? So I can turn that off. Caps, symbol protection off. Paragraph, emote protection. I guess we can allow that. All right, try again, Maddie, or whoever. Go ahead and try it. I turned it off. It should work now. Yeah, go ahead and try. Hey, what's the delay, by the way? Is it like quick? I think yesterday was like 1 second. Thank you, Chris. That is the correct spelling. Coulombs with a MBS. All right. Anyway, 10 times, or 4 times 10 to the negative 9, divided by the distance squared. Now the distance is 5 rad 2 centimeters. Okay, so that would be 0.05 rad 2 meters squared. And I have to square everything. And voila. Okay, go ahead and punch that into your calculator, see if you can do it. I'm going to use Wolfram Alpha. Wolfram Alpha is great if it works. Yeah, so go and punch in 9E9 times 4E negative 9, and you can see how the 9 and the negative 9 kind of cancel, so it's just 36 in the numerator, divided by the distance squared, so that's 0.05 rad 2 squared times square root 2 squared. Okay, and what do we get? I got something kind of big. 7,200. Now I kind of skipped out on sig figs. It looks like everything is 1 sig fig, so we can say that it's roughly 7,000 watt. Anyone remember the units for electric field? Well, there we go. Wow, that was quick. Newtons per coulomb N over C. Yeah. All right, so there you have it. Now, that is the magnitude. How do we find the direction? Right? The direction is a little bit trickier. E is along the same line as the displacement vector, or the hypotenuse. So basically, if I'm looking at it right, let's try that again. Okay. Well, we want to find the angle right here. Okay, how far down? Now it is a 5, 5, 5 rad 2 or 45, 45, 90 triangle. So that means that it is at an angle of negative 45 degrees. Okay, so it's downwards to the right, so that would be negative 45 degrees. Or you can add 360 to that and get the positive angle. Yeah. All right, let's take a look at the PowerPoint, and then we'll move on to our activity for the day, and then you can just do that, and that'll be it. It's a pretty simple day. PowerPoint, we did this yesterday, and so the next slide is actually the drawing. So the answer to yesterday's activity is right here on the slide. This is what it should look like. Obviously this is sideways, so if you tilt your head to the right, you'll see. So we have a plus and minus charge. It goes out of the plus into the minus. If you have two pluses, they repel each other away in all directions. There's this asymptote here in the middle, and so the lines bend. They don't actually cross that dotted line that I have. Right. If it were two minuses, it would look exactly like the two pluses, except those red arrows would be pointing inwards towards the charge instead of outwards away from the charge. So that was the only difference. The electric field lines. Okay, the electric field lines are electric lines of force, so they show you the direction of the force on a theoretical positive test charge. Okay, the lines are in the same direction as the force on a positive test charge. Okay, the lines always flow from positive charges to negative charges. So that's because, you know, a positive test charge would be repelled by the positive charge, and then the positive test charge would be, you know, attracted to the negative charge. So it goes away from plus and towards the minus. The strength of the field is indicated by the spacing of the lines. This is kind of important too. If we can go back to our OneNote. One way to show that the electric field is strong is to draw the lines close together. So let's say we had like a uniform electric field where we put a bunch of charges next to each other. Minus, 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 minus. Okay, if I did plus, 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 minus, 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 we know that the lines would go out of the plus and into the minus, and it would be nice and straight. This is how we get the uniform electric field. Now, one way to draw or show that the field strength is very strong is to draw more arrows, obviously, but make them closer together. So if you make them closer together, then you're seeing that the strength is high. So if you have lines that are curling and stuff, I don't know, depending on what you have around, you can have weird pictures. Pew, pew, pew. Okay, so near regions where the lines are kind of close together, of course, the electric field should be stronger. All right, back to the PowerPoint. All right. So lines are indicated by spacing. The field is strong where the lines are close together and weak where the lines are far apart. Oops, go and write all that down. While I pull up a simulator. Alright. Now, using this simulator, boom. Uh-oh. What's going on? Ah, there we go. Using this simulator, this is how we got the picture you may have seen on the board. This simulator draws out electric field lines. So I'm going to go ahead and activate the grid line. Where is the grid? Show grid. There we go. Snap to grid. That's also nice. Okay, I'm going to put a big charge, boom, which is +8, and then I'll put a -4 right above it. So now we have a unequal charge pair, so one of them is twice as strong as the other. So yesterday we did, 1Q and 1Q where the two charges are the same. Here we have one that is twice as big. So when I draw the field lines, the bigger one kind of pushes the electric field lines away from it, and it creates a nice heart shape. Whoa. Right. Okay, so this simulator just draws all the vectors one line at a time, figuring out the electric field strength from both, and then defining the resultant at every spot. Okay. All right, so back to the PowerPoint view. Let's go and try one more problem. This one, now we have two charges and we're trying to find the net electric field from both of them. Oops, my chair is kind of squeaky. Make sure you hit that follow button, and then you can type in chat. I made it so that you can only type after you follow. And I guess followers should also get notifications when the stream goes live. Here we are. Okay, so we have two charges similar to the one that we just did, but this one is microcoulombs. Charges are placed as shown. Find the net. Oh wow! Look, my Streamlabs is working. Nice. So 4 microcoulomb charges are placed as shown. Find the net electric field on X. All right. So let's go and draw that out on OneNote. Boom. And it's still a 5x5, except the charges are slightly different. Both charges are the same. So let's see, we have one here and one down here. And we're trying to find the net electric field. Oops, not very good. Net electric field at a spot that is also 5 centimeters away. So let's make sure, yep, that's it, 5 cm, 5 cm, 5 cm. All right. So just like before, where we did one force at a time between two charges, now we're going to do one electric field at a time from just a single charge. So let's go and label these. This is Q1, and this is Q2. I'll use different colors. Instead of red, we'll make this second one blue. All right. Okay. So again, the distance is 5 by 5. Oh, by the way, you should be able to see the YouTube link down below. Make sure you subscribe to the YouTube link as well. That's where all the VODs will be. But again, it takes like a couple hours, 1 or 2 hours to put the VODs up. All right. So it's a 5 by 5. We'll do it one charge at a time. Like so. Okay. We know that from the first one, there's an electric field based on this dotted distance. There's an electric field that points downwards to the right, and we'll call this E1. This is the electric field from the first charge. Okay. And what is E1 equal to? Well, E1 must be equal to K Q1 over the distance from charge 1 squared. So it's very similar to what we did last week, except now it's just one charge at a time. Okay. And we also, based on what we found in the last problem, we also know that this angle here must be negative 45 degrees. Okay. Now, similarly, this Q2 is also just as far, because this is also another 45, 45, 90 triangle. So Q2 produces its own electric field that points upwards to the right. Why is it upwards to the right? Well, again, Q2 is a positive charge. Both of these are positives, plus 4 microcoulombs. Q1 is plus 4 microcoulombs. Okay, so both of these are positive, and the arrows point away from it. So no matter where you are in space, the arrows that come from each charge point away from that charge. So red arrow is pointing away from the red charge, and the blue arrow is pointing away from the blue charge. And let me make sure I draw it same size. And I know that should be the same size because both charges are the same, and the distance is also the same. So E2 here, the blue one, is equal to K Q2 over the distance from charge 2 squared. Okay, so that's a subscript. Uh-oh, let me write it a little better, a little smaller. K Q2 divided by the distance R2 squared. All right, what's the angle for E2? Chat. Oh, we have 9 viewers now. Oh, great. People are finally waking up. The angle right here, this one, theta 2. What is theta 2? Wish I could do some polls or something. Do we need to class flow it up? Eventually we'll start doing like class flow, and then we'll even Kahoot it up. Kuya. Oh yeah, that's Casey. Good job, Casey. It is 45 degrees. Uh, 45 degrees. Okay. All right. So based on the values, we actually can see how the two arrows are pointing upwards to the right and downwards to the right. The y components actually cancel, leaving you with just the extra. That's all right. You can write DEG if you want. I don't know how to put the degree sign. So just write DEG. That's good enough. All right, so we have two vectors. Technically we're supposed to do components. So we do sigma E. So I'll do the long way just so you know the approach every time. But if you can see patterns, then you can definitely work smarter and not harder. Sigma EX, all of the electric fields in the x-axis. So that would be E1x plus E2x. Okay, so this is equal to K Q1 over R1 squared times the cosine of negative 45 plus K Q2 over R2 squared times the cosine of positive 45 degrees. Okay. Now, if you know your unit circle, of course, 45 would be rad 2 over 2. That kind of simplifies a few things. But if you don't, that's fine. You just plug and chug. So you get K, which is 9E9. 9 times 10 to the 9th. Times Q1. Q1 is 4 times 10 to the negative 6. Divided by the distance. We found the distance. It was 0.05 rad 2 squared. Chris, yeah, you gotta relax there, buddy. Cosine of negative 45. Again, that's rad 2 over 2. So let me write that instead. Okay, so this piece here. Plus 99 times 4 e negative 6, because the bottom one is also 4, divided by the distance. It's the same distance squared, times the cosine of positive 45, and the cosine of positive 45 is also rad 2 over 2. Okay. All right, and that should give you your answer. Smiley face. Of course, we always want to look for patterns. Doing it the long way might take too long. That's why it's the long way. So let's look for patterns. We know that the charges are the same and the distances from each charge is the same. Therefore, the values or the magnitudes of both electric fields should also be the same. Since they're pointing at similar angles, these symmetric angles, we know that whatever points upwards, ooh, that's not good. Whatever points upwards from, whatever points upwards from E2 will cancel out whatever points downwards from E1. So these two y component vectors will cancel out, meaning if I did sigma E y, I can just say it's 0. Okay, I can prove it. You just do E1y plus E2y, and you'll see that E1y is a positive value, E1y is a negative value, E2y is a positive value, and the two values cancel out. So we can take a shortcut and just say EY is 0. And we can see how the x components both point to the right. Let's use a different color. Boom. So the x component of E1, the x component of E2, they both point to the right, and they're both equal. So it's just 2 times the x component. Or you can add all of this up. So what is smiley face equal to? Yeah. Two times the x component of, well, whatever that is. Let's go and plug into our Wolfram alpha. So 2 times the x component of 99 4e negative 6 divided by the distance squared times rad 2. Oops. 2 times cosine of 45, which is rad 2 over 2. All right. So 2 times cosine of theta times k times 4 times 10 to the negative 6 divided by the distance squared, and that gives us 1.02 times 10 to the 7th, huh? Okay. You guys doing it? Go ahead and do it. Plug it in. Yeah. And then times what? Very good. Times 10 to the 7th. Okay. Now we also need units. So what did we find? What did we find? We found the net electric field. And so the electric field is measured in newtons per coulombs. Newton per coulomb. Okay. Now, since the y is 0 and the x is this value, we know that the net electric field which is the square root of ex squared plus ey squared, the Pythagorean theorem here. So that would just be 1.02 times 10 to the 7th squared plus 0 squared, and that essentially gives you the same answer. 1.02 times 10 to the 7th newtons per coulomb. And that is our final answer with nice 3 sig figs. Although I didn't use 3 sig figs in the number, so if I round this down, it would just be 1 times 10 to the 7th newtons per coulomb with 1 sig fig. I'll try not to use 1 sig fig numbers. Alright, that's enough for practice. You should go onto your Canvas and download the Phet simulation labs, and then you're just going to work on your Phet simulations. So when you download your file, it should look something like this. Bam, there it is. So go and download this Phet Lab. Go to your Canvas, look for 3/17, March 17th, and you should get this Phet virtual lab file, where you're supposed to go to the Phet website and play with the simulations and solve all of these problems. Go and answer it on here and then upload it to Canvas by Saturday. So this is due Saturday. Now the first part is actually just conceptual. It's before you actually play with the simulations. Electric charges can be positive or blank, negative. And you can answer those questions. This is the old equation, KQQ over D squared, similar to how you have it in your notes. Sorry, not your notes, your PowerPoint. I started using R squared so that all of our formulas have the same thing in the denominator. So there's a continuity between the equations. So again, D is the same as R, which is the distance from the center of mass to center of mass. Okay. The equation above is known as Coulomb's law. The force equation is Coulomb's law. All right. Anyway, let's talk about the simulations. For part A, okay, you have to go to Phet, Colorado, okay, and then go to, oh, this thing is still running. Let me close that. No wonder it's slow. If you go to the physics section of phet.colorado.edu, you can click on charges and fields. That's the same one I used yesterday. Under electricity, magnetism, and circuits, down here, you want to click on charges and fields. So go to physics, electricity, magnets, and circuits, charges and fields. Okay, and then hit play. And voila, here you have it. Today we want to turn on the grid and show the values. So put one positive charge at one block. Now you can see how in the grid, let me undo that. In the grid, you have like big grid boxes and small grid boxes. At the corner of the big grid boxes, place one positive charge, and then two big boxes later, put a negative charge. Okay, so that would be pretty much 1 meter. There is a measuring tape that you can use to measure this thing here. 100 centimeters is 1 yay meters. Oh no, it's too hard. I can't do it with my touch. But anyway, okay, so yeah, it's about 100 centimeters. Boom. All right, and finally, you're using the sensor, the yellow dot. The yellow dot will give you the value of the electric field. Boom. And it shows you the direction too. Whoa. Okay. And notice the units are slightly different. It says V over M. So that's the second way. So units for the electric field. We know that we can use newtons per coulomb. So that's the standard. But there is this alternative way, and this is also acceptable. And that is volts V per meters. Volts over meters. Where V is volts. And we'll talk about voltage starting tomorrow. Oops. and M is meters. Yeah. So once we get through the electric field, we'll get to voltage and potentials. That we'll start talking about batteries and circuits, and then some magnets, and then we'll be done with the year. So we're almost done with physics. Yay! Okay, so volts per meter is another unit for your electric field. And as you can see, the closer I get, the bigger this arrow becomes. It gets, really huge. Whoa, whoa. And of course, the direction changes. The direction is towards the negative and then away from the positive. Okay. Now you'll see that in the middle, between the positive and negative, you have the weakest electric field. This is actually an AP Physics 1 question. The closer you get to the plus, it increases. The closer you get to the minus, it increases. But in the middle, it's actually the lowest. Ooh. All right. So that's simulation 1. Using this, you should be able to answer all of these questions. Write down the values in your field, volts per meter, and then the ratios. Calculate the ratio of the field when the distance is doubled and get the average. So you double the distance, of course, you get 1/4 of the field, 1/4. And number 7, this was kind of hard. If you didn't read your textbook, you should be reading. Your eyes hurt? Why? For the simulator hurts your eyes? Oh. This shows that electric force and therefore the field and distance are related by an inverse square. Inverse square. Can I write? Pens. Okay. Inverse square law. Yeah, that means because the formula is 1 over r squared, so times k times q. This is called an inverse square law. Okay, and force is 1 over r squared times k times q2, but both of them have this 1 over r squared. Oh wow, spamming caps. Oh yeah, auto caps. 8 messages were deleted by moderator. Wait, 8 messages? Wow. Wait, what are you trying to type, Maddie? Oops. Let's turn that off. Oh no, it always crashes. Every time. Oh well. The second part is actually the same thing we did. So go and draw negative and 1 positive and then 2 positives. Basically the same thing we did yesterday. But you don't have to do 16 lines. Just do like 8 or something. Do 8 lines. Simulation 2. We're going to do John Travoltage. Ooh, John Travoltage. If I go back. This one. John Travoltage. And you have to play with John Travoltage a little bit and then answer some of the questions. So here's John Travoltage. What you can do is, rub your feet against the carpet. Now, if you're using shoes, it's not the best. If you do this with socks, it works really well. So charge until you've built up enough charge. Eventually those charges will kind of move away from each other, make your entire body negative. And then if you have enough, it'll go through your hand to the closest conductor, and that's the doorknob. So you might get zapped. So you'll notice that sometimes, when you try to open your door, you might get shocked. That's called static shock. Or if you're coming out of a car that has like cloth seats or something, or velvet seats, and then you're coming out of the car and you touch the door, you might get shocked. So, John Travoltage, kablamo. Now, if I move the hand closer, I don't need as many charges. Ooh. Of course, the further out you are, all the way to my nose, I'm going to need a ton of charges. Let's see if we can get it. More. Come on, John Travoltage. Oh, it's going into my brain. This is not good. I think I maxed it out. Alright. Oh, we're getting close. No, I can't. Oh, there it is. I guess there's a limit to how many charges. Alright, so play with John Travoltage and then answer these questions here. And then do a quick summary. Okay? Any questions? I'm about to close our stream, so questions now would be great. If you have questions for Mastering Physics, this is the time. Because Mastering Physics is due today. Alright, well, I will stay on. I'm just going to turn off the stream and then restart. So I'll stay on, and if you have any questions, extend the Mastering Physics? No. Isn't there like only like 20 questions? Yeah. Alright, we'll see. Do as many as you can. I think they're pretty straightforward though. Let's see. Oh, I got logged out. Dang it. Yeah. Assignments. You're talking about the one that is due today. But that's all just force stuff, right? KQQ over R squared. It's not really electric field stuff. You do have to do some vectors, I suppose. He seems depressed with all the negativity. Pretty good, Maddie, pretty good. Extended for people who are lazy. Why should we do that, Chris? John is an electric man. Right. I mean, I think we should be able to do it. There are some conceptual ones. Let's see. How about the bumblebee question? Bumblebees and static cling. So this is 19.106. 19.106. It says Ben Franklin showed that the same kind of spark we experience when touching a doorknob, perfect question, after walking on a carpet is a bolt of lightning if it is scaled up in size. His insight, and if you remember when we used the Van de Graaff machine, and then if you remember when I was touching it, and then if you try to get close to me, you get shocked. So that's basically a lightning bolt going from me to you. So Ben Franklin says that, yes, this is actually a lightning bolt. Oh yeah, your hair. That was perfect, Maddie. Chris has too many electrons. Ooh. His insight led to the invention of lightning rods to conduct electricity safely out of a building and into the ground. Today we employ static electricity in many technological applications, ranging from photocopiers to electrostatic precipitators that can clean emissions from smokestacks. Static electricity plays an important role in the pollination process. Imagine a bee busily flitting from flower to flower. As air rushes over its body, it acquires an electric charge, just as you do when your shoes rub against a carpet. A bee might have only 93 picocoulombs, so maybe, I know your number might be slightly different, but 93 pc, p is pico, and p is 10 to the negative 12. It's the one right after nano. 93 picocoulomb. So this would be 93 times 10 to the negative 12 coulombs. But that's more than enough to attract grains of pollen from a distance. Like a charged comb attracting bits of paper, the result shown in the picture is a bee covered with grains of pollen as she travels from one flower to another. So the next time you experience annoying static cling in your clothes, just remember that the same force helps pollinate the plants that all animals on Earth, including humans, rely on. Ooh, if it weren't for these bees, we wouldn't have honey. Man. Alright, anyway, the actual question, it says, the force required to detach a grain of pollen from a stigma of an avocado flower. Ooh, without bees, we wouldn't have avocado. And I definitely love avocados. Avocado flower is approximately 4 times 10 to the negative 8 newtons. Okay, so that's the force. What is the maximum distance at which the electrostatic force between a bee and a grain of pollen is sufficient to detach the grain? Treat the bee and the grain of pollen as point charges and assume that the pollen has a charge opposite in sign and equal in magnitude to that of the bee. All right. So basically, the bee is some sort of positive charge. Okay. And we're saying that the pollen is some sort of negative charge. Okay, and there's a certain distance between them, r, and that's what we're trying to find, based on the fact that the force needs to be, in this problem, it says the force needs to be 4 times 10 to the negative 8. Okay, so this is simple plug and chug. It's just a lot of reading, really. Force is equal to K, Q1, Q2 over R squared, and we're solving for R, so isolate, eat your vegetables. R is equal to square root of the force times, nope, I did it wrong. R is equal to the square root of K times Q1 times Q2 divided by F. You can do the old swap-a-rooney, just swap whatever's here with whatever's on the left side. Okay, that's because we put a 1 here and cross-multiply. Okay, so now it's just plug and chug and then solve for R. So you get square root of 9e9 times Q1, which is 93e negative 12 times 93e negative 12 divided by the force. The force is 4 times 10 to the negative 8. And make sure the entire thing is inside the radical. And that should give you your answer. Yay! Alright, that's it for today. Thank you for tuning in. I'll see you next time.